In this short lecture, we are going to see a little bit more of sheaves from the categorical perspective. Now, sheaves were defined as functors, so already there's a ton of category theory involved just to define them. But I want to talk more about sheaves, the collection of sheaves over a fixed simplicial complex having the structure of a category. So let L be a simplicial complex. And consider two sheaves, S and S prime, sheaves on this L. So if we want to build a category of sheaves on L, we need a good notion of morphism from S to S prime. And by this point in the course, I don't think the definition will be surprising to anyone who has been paying attention from, I think, week 4 onwards, but let's see what it is anyway. So a morphism of sheaves, which let's call it phi, from S to S prime, is a collection of linear maps that are going to connect the stalks. So phi tau is going to go from the stalk over tau of the first sheaf to the stalk over tau of the second sheaf, and you have one of these for every tau in the simplicial complex L. So you have a way of pushing the data over the stalk of tau to the with respect to the sheaf S to the corresponding stalk for the same simplex of the sheaf S prime, so that anytime you have a phase relation, let's say tau 0 less than tau 1, the following diagram commutes. And hopefully, you know what the diagram is without me having to draw it, or before I draw it, so you have a minute. Commutes. Okay, now that I've written commutes, you no longer have a minute. Here it is. So there are 4 things involved. There's the stalk of tau 0 and the stalk of tau 1 with respect to the sheaf S, and then the corresponding stalks with respect to the sheaf S prime. And there are 2 maps that come from the sheaves themselves. So this is going to be the restriction map of the first sheaf, and this is going to be the restriction map of the second sheaf. And now our 2 maps, phi of tau 0 and phi of tau 1, are transporting all the data from the left, including the vector space and the linear maps, to the stuff on the right. And of course, we require this diagram to commute for any pair tau 0 less than tau 1. And you should check that these morphisms endow the set of all sheaves over L with the structure of a category. And we will write that category as sheaves over L. So SH of L. And of course, what does check mean? Check means you have to define how you should compose 2 of these morphisms of sheaves, S to S prime to S double prime. How would you compose it? Well, the diagram is the big clue. You just tack on another commuting square to the right of this, which connects the stalk and the restriction map of S prime to the stalk and restriction maps of S double prime. And the fact that the 2 squares commute means that the giant rectangle will also commute. So that's how you compose things, just simplex-wise. Okay, so the goal in this lecture is not just to look at this category, but to define functors that relate sheaves over different simplicial complexes. And so what I mean by that is that this category is really, really nicely behaved, the category of sheaves on L, with respect to simplicial maps. It's nicely behaved in 2 different ways, which I'd like to show you now. So our goal is, given a simplicial map let's say f from some simplicial complex k to some simplicial complex L, produce two functors. So one is going to go sheaves on L to sheaves on K. So this is going against the direction of the simplicial map. And another functor that's going to go in the correct direction, in the same direction as the simplicial map. And so this one is called the pullback because it takes sheaves on L and pulls them back against the direction of F to sheaves on K. And the other one is going to be called the push forward, which pushes sheaves forward from K to L. And so that's our goal in this lecture. It's just defining these two functors and saying a little bit about what their properties are. These are very, very useful for a whole bunch of reasons. So for instance, our theory of barcodes only applies to assignments of real numbers to simplices. So if you had L, this space getting sent to real numbers with a monotone map, then you'd have some barcodes for L, and then you could take the simplicial map and push it forward to get a barcode for the simplicial complex K. So what I mean is, if you have a monotone map L to R, we get we can always push it back to getting a map on K. And what we'll be able to do is figure out the barcode of K directly from moving a certain sheaf around. So let's see what these two functors are, the pullback and the push forward. And the pullback turns out, surprisingly, even though it's going against the direction, the God-given direction of F, it turns out to be much easier to define. So given a sheaf S on L, its pullback across, used the wrong color, haven't I? So its pullback across the simplicial map F is a new sheaf, which of course we're going to write as F upper star S on K, defined as follows. So to define a sheaf, we need to send simplices of K to vector spaces. So let's say sigma is a simplex of K, and we want to know what the stalk of our new sheaf is. Well, it's just going to be S of F of sigma. Remember, F of sigma is a simplex in tau, and there's one thing that the sheaf S knows how to do, which is assign vector spaces to simplices of tau. So this is very nice and easy. And so this is for all sigma in K. And now we need linear maps for all sigma less than sigma prime in K. And those are also easy. So F star S of sigma less than sigma prime is just the linear map. That's, again, the restriction map of the sheaf S after pushing sigma and sigma prime along F to the simplicial complex L, where now the sheaf operates with impunity. Like the sheaf S can send any face relation, and because it's a simplicial map, you know that F of sigma is going to be a face of F of sigma prime. So this, okay, there's a little bit of work. You have to check that it satisfies the associativity axiom, but that's easy. I mean, it inherits associativity from S, so it's going to get all the properties you want from S. So this is one sheaf morphism. So it's going to take sheaves on L and produce sheaves on K for you against the direction of the simplicial map. If you want to go forwards, this strategy that we used here is not going to work because F is now working against us. For every simplex of L, there might be a ton of simplices that lie in its inverse image, its fiber. And we've already defined the fibers, so we know something of what they look like. So so we cannot use this, right? If we replace f with an f inverse, there's no stock associated to f inverse of a given simplex in tau. So here's what we do. We define the push forward using the étale space. So same setup as before, except now we have a sheaf. Let's call it T on K. It's push forward across our simplicial map, which remains the same. F, K to L is a new sheaf, which I will write as F lower star of T on L, whose étale space equals, so I guess we want to write étale space of F star tau. So remember, it has to be pairs of this type, where you have a point in the geometric realization of K, and then you have a point, of L, and then you have a vertex a vector in the stalk. So it's going to look like this. F x v, where xv lies in the étale space of tau, of T rather, the sheaf. So let's see what this means carefully. This means that V is a vector in the stalk of the simplex, the unique simplex containing X in its interior. And this is the image under F of that point X. And remember that the F with the bars, which I may as well write, where F is the continuous map induced by the simplicial map. So if you go back to the definition of the étale space, you will realize that this is a very, very convenient definition. So in the sense, note that the stalk of F star T over a simplex tau is precisely the space of sections over the star of that simplex tau with respect to the sheaf T. So that's an exercise. If you don't see it right away, then you should try and prove that that's what we just did. Okay, and what is the point of all this? Well, there's a theorem that F star, which goes from sheaves over K to sheaves over L, and F star upper star, which goes from sheaves over L to sheaves over K. So this push forward and pull back form a pair of adjoint functors. And what that means is for every sheaf S on, so let's, instead of saying on, let's use the category. So every sheaf S over L, and for every sheaf T over K, there's a bijection of some sort. And here's the bijection. Morphisms from F star, the upper star, S to T, in sheaves over K are the same as morphisms from S to F lower star T in sheaves over L. So one way to think of these is sort of as transpose matrices somehow, and I realize that that's going to sound vague, So the point is that knowing a morphism of this type, a morphism from the pullback of S to T is the same as knowing as a morphism from S to the push forward of T. So how does this work? Well, I will give you a hint about how this works. So you can use the definitions of the pull back and the push forward that I've given here. There exists very natural maps of sheaves of the following type. So there's a map that goes from S to F star S, so lower and then upper, and another map that goes from F upper star, F lower star, T to T. So you have to find them. Once you've found them, these are magic maps. I'll just label them like this. Once you've found these two maps, then given any morphism of this type, you apply F lower star, and that gives you F lower star, F upper star S to F lower star T. And now you can always append the magic map, the first one that you found, to get something of the type on the right side, which is a morphism from S to F lower star T. And similarly, the other magic map gives you a way back to go from S to F lower star T back to F upper star S to T. And these are going to be inverse functions between the sets of morphisms. Okay, that's all for this lecture, and in fact for this week. Next week we will talk about the biggest hammer we have for computing all sorts of homology and cohomology very, very efficiently. This will cover ordinary homology, ordinary cohomology, sheaf cohomology, persistent homology, all of these. So there's one ring to compute them all, and that will be the subject of the final week of the course. I look forward to seeing you there.